very interesting because it's unaffected by linear transformation and it represents the limiting behavior of any random process after aggregation, after averaging over increasing time spans. Okay, so let's just move to another distribution then. And the second one that I'm considering is very simple. It's the uniform distribution. The uniform distribution in terms of probability density is given simply by a segment covering a range of the real axis between A and B. I forgot to say, sorry, this is important. I'm talking about distributions for continuous variable. This is implicit because I'm talking about densities, but these are, it's better that I emphasize, these are distributions for continuous variable. The Gaussian is not for discrete variables. So the uniform distribution, again, let just me clarify the physical meaning. First of all, it is bounded. So it takes value only between A and B. And within this range, it gives uniform probability. You see here the density is given by 1 over B minus A. Which means that simply if you take the integral, you obtain a segment that is starting from 0 cumulative probability in A ends to 1 cumulative probability in B. Understand that in hydrology is not really useful because we don't have data that are equally likely, but still it's very important for applications and we will see why. Okay, now let me perform a couple of experiments. Now, I open the R, I hope you can see. First of all, R has a function that allows you to generate data following the Gaussian distribution. And this function is, let me give, for instance, to the name of a variable, Gaussian. Function is R norm, which means random normal, and you have to give 3 arguments to the function. The number of numbers that you want to generate. I want 1,000 outcomes. Then the average and the standard deviation. And let's look at the plot Gaussian. And let me just use the line, because otherwise This is the plot. So you see the observations. They are all very close to the mean, and they are extended between, remember that the mean was 0 and the standard deviation was 1. They are extended between -3 and +3 basically. Remember that I said that in the interval, I deleted, but in the interval minus, in this case, -2 + 2, I said -1.96. So between -2 and +2, you should have 95% of the observations. And indeed, you see that most of the observations are located in the interval that I said. Let's make a check. Let's make a check. Let's count, estimate the percentage, compute the percentage of observations that are within the interval that I mentioned. So let's write length Gaussian and look at the formalism that I'm using. So if Gaussian greater than -1.96 and Gaussian lower than 1.96. So look at this instruction. I'm computing the length of the vector Gaussian by making a selection over the vector. The selection is to be given between square parentheses and counts two conditions. Gaussian greater than -1.96 and Gaussian lower than 1.96. And given that I want to compute a percentage, let me divide by 10. It should be divided by 1000 and multiplied by 100. So this is the result of this computation. If I didn't make any mistake, should be 95.6. So you see that indeed, of course, you don't strike 95 because you are generating numbers. But you see that the uncertainty is very reduced. Good. But now we could be curious and try to compute the probability density and see if it looks like the function that I observed before. Now let's try to estimate the probability density. And let me make clear what we should do. I generated a series that, as you have seen, is comprised between more or less -4 and +4. If you look at the max Gaussian is 3.1, and if you look at the minimum, it's -2.8. You see the symmetry there is between the maximum and the minimum. In absolute terms, there is almost no difference. So let me, if I try to visualize on my axis my data, I should go between -3.5, 0, and 3.5. And let's suppose that I want to compute here my PDF. So what would be a way to compute it? And You remember I said I should take around a given value an interval. And of course this interval, if I want to estimate the probability distribution empirically, it should have a finite length. So let me consider these intervals. 3 minus 3.5, 3. So let me see. 3, 1. Minus 3, minus 2.5, minus 2, minus 1.5, minus 1, minus 2.5. These are my intervals. It's not really clear, so I feel that now. So I have 3 here, this is 3, then I have 2 and 1. And let me put also here. Now, let's consider the first interval, which is this one. I should count how many data fall in here, and I have already seen that the number is 0, because the minimum is minus 2.8, 2.7. So I should count the number of data here. So let me indicate this number as n1, and then I should visualize here, I should compute the quantity n1 divided by m, which is 1000, divided by 1.5, because this is the length of the interval, sorry, the width of the interval. So if you remember how I defined the probability distribution, probability density function before, I said I have to compute the number of data that fall within each segment, divide them by the total number of numbers, and divide them by the width of the segment. So the width is constant in this case. Yeah, please. You have a question? Yeah, okay, because the question is you divide it by 2 delta Q in the previous formulation. But because in the previous formulation I assumed that the width of the interval was 2 delta Q. In this case I assume that it's 4.5. So before I just give a symbol for the width. In this case it's a number. Because I need to make the computation now, so I need to fix numbers. And in this case my delta Q will be 0.25. So this is the estimate of my probability density that I can put here. And then I have to compute n2. And then n3, etc. So let's try to make, and look, when you make the plot, if you want to plot these points, the x value to plot is the center of gravity of the interval, is the midpoint of the interval. So if you want to display a graph, you cannot locate the probability density at the lower bound of the interval, and neither to the upper bound. We have to locate the probability density in the middle. Is that clear? Okay, so let's make the computation. And let's write n1 equal to. So we need to write length. We have to count n1 first of all. So this is not n1, it's p1. I have to count n1, so length Gaussian, and then I have to put the conditions to make the selection. So Gaussian should be, it's between minus 3.5 and minus 3. So Gaussian should be greater, than minus 3.5, and Gaussian should be lower than minus 3. I close the square, I close the round parenthesis, and then I get the length, which is n1 I have to divide by 1000, which is the total number, length of the vector, and then I have to divide times 0.5. This is P1, and it should be 0, 0. Okay. Now, let's compute P2. And now I have to move to minus 3.0 and minus 2.5. P2 will be different from 0. You see that it's different. Okay, now P3, we need some patience. P3 minus 2.5 minus 2. P4 minus 2 minus 1.5. P5, sorry guys, I move forward as quickly as possible, but we need to make every computation. Minus 1. Strictly speaking, I should put sometimes minus and sometimes minus or equal, but we are dealing with real numbers, so we can avoid the equal sign. P6 minus 1 minus 4.5. P7 minus 1.5 and 0. P8, sorry. 0 and 0.5. P9 5, 1, P10, 1, P10, 1, 1.5, P11, 1.5, 2, P12, 5, P13, 2.5, 3, I am almost finished. P14, 3.5. You can stop here. Okay, now let's try to make a plot. So, yes. Yes, but because the first one was mistaken. And the first one was, okay, thank you very much. Thanks a lot. Now let me make the plot. First of all, I have to put the x-axis, the abscissa is given by the midpoint of these intervals. So let's be patient. The first line is minus 3.25. Look that I am defining a vector. So plot, I open two parentheses with the C in between. Minus 2.75, minus 2.25, minus 1.75, minus 1.25, minus 4.75, minus 4.25, and then I can, let me try to make a smart move, if I can conceive a smart move. No, it's not really smart, because I should rotate it, so it's better if I 4.25, 4.75, Okay, and now I have to put my probabilities. C, it's, I think it was P1, P2, okay, type equal line. Let's put LPD equal 2. I want a thick line and color equal red. I'm not sure everything is correct. I just try to press enter and see what happens. It seems that we got a graph. Yeah, this is the graph. And you see that, of course, there is some discretization, but you see that the picture is quite symmetric. Now, you may ask me, but every time I need to do this? No, because we have a function in R which computes the density. So now the trick is to try to ask R to compute the density and to see if we get a similar density. And first of all, look at the curve and please consider that usually, not usually, always, this is a strict condition, the integral of the probability density function, which means the area below the curve, should be equal to 1 because it's the cumulative probability over the whole range. And if you look at this area, you see that the top y is 0.4 and the extension of the base is more or less 4, a little bit less than 4, so 0.4 times 3 would be 1.2. I think it's indeed 1, the integral below the curve. Okay? And now let's ask R to compute the density. R is much more precise than us, and he uses more intervals than us. So you would expect a curve that is not so spiky as this one. And also it applies some regularization, so you don't see the corners. But anyway, I think it's interesting to see if they more or less overlap. So, lines, density, Gaussian. That's it. Let's look at the graph. Perfect. It's indeed perfect. Again, this is the instruction. Lines, density Gaussian is the instruction. Density gives, as a result, an x and y. If you, for instance, if you try to like trial equal density Gaussian, and you try to see what is a variable trial, you see that you have some specifications and some of them, let's not to forget, to be concerned, and then you have x and y, and therefore these two, I think also we should get. Yeah, you see that if you, because if you just write trial, it gives to you a synthetic output. It doesn't give in output everything that he has memorized under this variable. And you see that there are two sub-variables, x and y, for which it gives to you the minimum, the first quartile, the median, the mean, the statistics that, let's forget about that. But it doesn't give you the value in x. But if you just press trial and then, because this is a list, I'm not sure I introduced to you the list so many, no. But basically, R has the opportunity to store sub-variables under variable names. which means that if you have three vectors and you want to put them together, not in a matrix, but in a variable that can distinguish, a variable that is subdivided in three subsectors, you can do that. It's a list. And basically the list has some names, and if you want to get the sub-variables, you just have to put a $sign and then the name of the sub-variable. And you see that here you get 500 values, which are my x. And if I did trial y, you have again 500 numbers that are my y. Let me just to explain to you, because I take the opportunity to introduce lists. So let's suppose that you want to create a variable that has sub-variables, not a matrix, because the sub-variables can be character, numbers. So let me do that. And let me define trial equal list. Okay? In this way, you tell R that you want a list. You want trial to be a list. And then you can write like trial dollar sub-variable 1 equal to, for instance, C 1, 2, 3, 4. Okay? And then you may say, okay, trial sub-variable 2 equal, again, C, a vector of characters R, B, A, B, C. Okay, now if you just type trial, you get the list 1, 2, 3, 4, A, B, C. This is useful because sometimes you may want to compact some similar variables like a vector and the names of the elements of the vector. You want to compact them within a list. Okay. Now let's go back to our statistics and our plot. You see that indeed the definition that I provide to you is correct. Look, if I go back to my trial density, Gaussian, I just want, oh sorry. I just want to take the opportunity, I computed the density. So, as you know, I obtain the list, and I can plot it, plot trial. Because given that in trial you have an x and y, if you plot the list, automatically the plot function recognizes the x and y and plots it. Now let's suppose that you want to compute, to plot the cumulative distribution, not the density. And I said that the cumulative distribution is the integral of the density. So probably you are getting concerned, no, an integral, how can I compute an integral? It's very easy. Let's see. First of all, let's consider that I will obtain the same result if I go plot trial x, trial y. Same result, which different, it uses points in this case, but the same result. Now, if I want to get the cumulative density, x doesn't change. What changes is y. That should be not the probability density, but the cumulative sum. The integral is nothing else than the cumulative sum of y. And therefore, let me do that. It's very easy. Cum sum. Look, this is our CDF. And it's not really, how to say, it should be a scale, because you see that there is a scale problem here. It integrates to 70. It's a scale problem because of the way in which it's computed in R, the cumulative density. But if we integrate hours, let me go back to the plot that I did before, my first plot. This is, if we integrate hours, we don't need to rescale. And first of all, our plot is this one. Let me see, because, okay, let me try. And first of all, let me create the vector. Because if I have to rewrite this, I become bad. So let me get this vector. And this is PDF equal C. So I created a vector, and let me create also a vector for the y-axis. For the x, sorry. So now if I want to get the plot of the PDF again, it's just enough to write plot x-axis PDF, and you see the graph. It's like before, the only difference is that I didn't take the... And let me see, just to see if the integration probably it's not really PDF. Let's see. No, it sums to 2 because yeah, even in this case there is a scale problem. Because you know the discretization is yeah, it sums to 2 because when you make the integral of numbers computed in this way, of course you have the width of the interval that matters, because you know, let's suppose, I just want to explain to you why it doesn't integrate to 1, and you need in any case to rescale. Let's suppose that you have a theoretical PDF which is extended between -4 and 4. And you have this theoretical value, this is 0. And let's suppose that you make a discretization that is very wide, so you get a point here, one here, and one here. And you compute a sum, okay? And I assumed obviously that it should be, the cumulative sum should be 1. This is not really correct because if you then decide to increase your discretization, and you do like this, like this, like this, you increase the amount of the numbers that you sum. So of course you get a sum that is higher. So at the end you need to rescale in any case, because the discretization introduces this error in the computation of the cumulative sum. So basically, to go back to our density computed with R, what I should do is to plot this. And now we are okay. You see that what I did basically is just to divide the cumulative sum of numbers by the total sum of the same numbers. And then if you look at the graph, I just switch to the graph, you see that it sums to 1. This is indeed the CDF of the Gaussian distribution, but I had to rescale it. And I just want to show you these computations because it's a chance for you to learn how to handle R, how to move yourself within R. Okay, now let's look at the uniform distribution. I mentioned that there is this uniform distribution, and let's generate it. Uniform 1000, 0, 1. Sorry. Uniform equal to R unif. The function is R unif. And of course, I have to give the number of elements that I want to generate. And you remember that the uniform distribution has two parameters, A and B, and 0, 1. And let me plot it. Plot uniform type equals line. Let's see how it is. Basically, one could say that you don't see a big difference with respect to the Gaussian, just looking at the data. Indeed, there is some difference. If you look at the range, it's between 0 and 1. There is no number outside this range. And also, the big difference is if you compute the density. I'm not computing the density manually now. I'm just using R to show you what is the density. Plot, density, uniform. Let's look at the plot, the resulting density. This is exactly what you would expect. And be careful, you see that it's not really a segment. Okay, there is some fluctuation. This is because they are numbered. And also you see that indeed it should stop up there at the lower bound of 0, while here you have the graph that is prosecuted to get a value that is lower than 0. This is just a misrepresentation by the graph, by the graphical routine. Because the graphical routine doesn't realize that it's a uniform distribution, so it tries to, to make it more regular.